Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to take a look on the modeling of material nonlinearities approximately in Autodesk Robot. I'm saying approximately because, fun fact, Autodesk Robot is unable to model material nonlinearities as it is known in scientific research. However, for practical reasons, you can still consider material nonlinearity using nonlinear hinges, and this is what I want to talk about today. It's basic nonlinear hinges coupled with something called pushover analysis. So I hope that you enjoy this video, and of course if you enjoy this video, why not give it a thumbs up and subscribe to this channel. It helps a lot to increase the reach of my channel. Now this is going to be kind of an introductory video, which means that there will be follow-up videos with full structures. Now in this video I'm going to model me a simple 2D frame and a simple beam to explore the abilities of robot to model material nonlinearity. Of course, before I start, I have to give you a brief introduction about material nonlinearity. So to do that, I need to open Paint. So I basically drew me some stuff on Paint to explain what I want to say. Now the first thing I want to talk about is the stress strain diagram. Now this is, once again, you need to check out your mechanics of materials courses if you want to get a deeper understanding of this. But the bottom line is strain and stress behaves linearly in something called the elastic range and non-linearly in something called the plastic range. Now in the actual stress strain curve is different, but we usually, as civil engineers and even researchers, do have our own simplification, which could be a simple bilinear relationship or any other relationship of the liking. Now, of course, the relationship depends on the code. You could, for example, assume something like this. Or you can, for example, assume something different like this. Now, this is really nice. I personally love this topic, to be honest. But, of course, it depends on the kind of code that you use to model your nonlinear behavior of steel. Anyway, so what I'm saying is that material, if it passes through the elastic region, then you start doing the plastic region. In that case, you have a different material characteristic, which means basically that your material is yielding and that you have a weak point in the structure. Because you would have, for example, for flexural moments, you would have a plastic hinge developing. Speaking of which, I'll be focusing on beams today, so I'm focusing on something called the plastic hinges. Now, a beam is a flexural element. If you're in the elastic region, you get the elastic stress response. If you're in the plastic region, you get the plastic stress response. Notice that the plastic stress response here is equalish in both points. This point is equal to this point because this plastic stress in the section was assumed using the orange line. Of course, if I want to use, for example, the blue line, I would have the following stress strain diagram, which would look something like this for the blue line, something like this to a field, and then you would have some strain hardening in the plastic region. It depends basically on the type of stress strain diagram that you are assuming. Now, basically, this is, I remind you, this is the stress distribution on a cross section under positive moment, and this is something I will be talking about. So, well, what ends up happening is that the structure actually reaches something called the plastic point, and when the beam section has fully plasticized, then you would have something called the plastic hinge, which means that the plastic hinge is not going to be able to carry any extra moment, or basically will only carry a little extra moment, because it no longer is able to develop any extra stresses depending on your model. If it's a bilinear, perfectly plastic model, then, well, the stresses don't increase at all. If it's a model with strain hardening, then the stresses might increase. Of course, you have also the option to cut off your stress strain diagram, which simulates the breaking, meaning that if you cut it off like this, then it means that in that case the section will drop to 0 because you assume that the section has been fully damaged. And this gets a little bit weird in terms of structural analysis. All right, so I hope that this theoretical background helps you understand what material nonlinearity is in terms of bending elements. So with that being said, let's model us a bending element. So to do that, I'm just going to model me a simple frame. Of course, this problem is two-dimensional because it's easy for me to explain two-dimensional problems. To deal with three-dimensional problems would be something in the future. I'm thinking of having a water tower and show you where the weak points in the water tower are. But for now, I'm just gonna basically assume me a two-dimensional frame. So I just put my grid like this. I'm gonna select me a beam. I'm gonna select me a steel beam, basically a beam or any of the liking. I'm gonna select me a smaller beam. I'm gonna choose W10 by 12. The reason behind choosing this beam is because I have prepared some calculations beforehand for this beam section, so I'll be using those calculations in a moment. Anyway, I'll just add that, close, and then I will use this beam to draw me, or basically the entire frame. So I'll just click 1, 2, 3, 4, and close that. I'll add me two fixed supports here, and that's it. I think we have finished modeling. Now, of course, let me explain what I'm trying to do right now. Now, you could perfectly just add you a force. I mean, I'm just going to add me some case here. Now, this is only a dummy case. My reason here is only I want to show you how those nonlinearities happen rather than to discuss the forces now. Just show you what happens if I add a 1 Newton force. So I'll just add me a 1 kilonewton force or something. So if I add me a 1 kilonewton force on this node, you will see that you have the typical moment diagram that is basically loading the columns, and of course the beam would have a linear moment diagram too. You can see this like this. Well, this is perfectly fine and is what we are expecting to see. Of course, if I keep increasing the forces, then the forces will increase, which will in turn increase the moments on those joints. And in one moment, or at one certain force, the joint will be loaded so much that the cross section at that joint due to moment will yield and actually will fully plasticize. And you can do that. You can let robot actually mimic for you a full plasticization of a cross section. Now to do that, you go to geometry, additional attributes, and select on nonlinear hinges. As the name suggests, it's a nonlinear hinge that takes into account the nonlinearity of stuff after you pass the elastic range. Now you have axial, shear, and moment hinges. I'll double click on seal moment hinge to show you what is defined there. Of course, you can define any type of nonlinear hinge. This is predefined. I'll click on the definition of the hinge model. And you can see in the definition of the hinge model, it's really peculiar and fantastic, to be honest. You see that you have an axis, which is your moment value, an axis, which is your rotation value. This corresponds to stress strain because when you rotate stuff, you get a moment. Similarly, when you strain stuff, you get stresses. And you can see that there is a linear proportion, and those values 1 and 2 was -1 and 10 and -10 are ratios. The ratio of the current moment applied on a point divided by the limit moment. And the limit moment is the plastic moment of the section. And I will prove that to you in a moment. So M is what kind of moment you have on the joint, and M limit is the plasticization moment or the fully plastic moment of the section that you have. Similarly, R is the rotation you have currently on your node, and R limit is the limiting rotation that produced a stress that was yielding, that fully plasticized the section. So R limit produces M limit. You can see that at 0 to 1, the stress strain curve, or basically here the rotation moment curve, is perfectly linear. This makes sense because nothing has plasticized. Now when you reach the full 1, then you would have a fully plasticized cross-section. And of course, I told you before that you could have a simple bilinear relationship that is perfectly plastic, or a simple bilinear relationship where there is some strain hardening or some any other form of relationship. Now you can see that here that you have almost a bilinear relationship with a little bit of strain hardening, and there is a full drop in the moment capacity, and in the end it dies actually, meaning that after you pass a certain rotation limit, the joint will no longer carry any moments, basically. It will lose all its resistance. Now, this curve is, I think, based on codes, and you would have some codes, for example, AISC, the steel code, or even the Euro code to guide you with this. If you're unsure, you can basically make a fully elastic, fully plastic, or perfectly elastic, perfectly plastic stress strain curve, or in this case rotation moment curve, and nobody would blame you because this is the most simple you can get. Anyway, I'll use this to define me two nonlinear hinges. Now, where do you expect nonlinear hinges to occur? You expect nonlinear hinges to occur in the middle of the beam because this is where the positive moments would be maximum, and at the connection points because this is where the negative moments are maximum. Now, I'm not going to define me anything in the middle of the beam because I'm going to apply forces that are horizontal, which will yield, or which will give us the moment diagram that you see here. And in that case, you can see that there is almost zero moment in the middle point. So It doesn't make sense to add a plastic hinge in the middle point. You can do that if you want, but I'll just leave it for no. In structures, in future structures, I will add a plastic hinge in the beginning, a plastic hinge in the middle, and a plastic hinge in the end of each and every beam. But for now, because I know where the moments are going to happen, I will just basically add me a plastic hinge here and a plastic hinge here, because this is where I'm expecting moments to be maximum, as you can see, and I want to see robot's plastic nonlinear hinge in action. So okay, I'll just add me a moment hinge. Of course, what I explained the moment is also the same in shear and in axial. The difference being that in moment you have rotation versus moment. In axial you have displacement or strain versus force. So I click on moment, I click that. So yes, I just add me a plastic hinge. You can see this red dot, and ask me a plastic hinge, which you can see this is the red dot. Now if you run the analysis, nothing will change, to be honest. And this is a little bit rather like surprising. Like nothing has changed, although you have plastic hinges. The reason why nothing is changing almost is because, I mean, your force is harmless, so it will not produce any plasticization effects on the frame. Of course, you can increase this force to just check out what happens if the structure plasticizes or the section plasticizes. So let me just put a ridiculously big value just to show you the point. So I'll just add that. I run the analysis right now and show you that, well, hopefully the forces are too much and the plastic hinge develops. Let's take a look. It seems promising. Let me just normalize. Ah, yeah, you see, now the plastic hinge has developed here, and you can see that this point no longer carries any moment. Now, I know what you're thinking. You're thinking that this is not how plastic hinges work. When a plastic hinge works, it only carries its plastic moment. It doesn't carry a zero moment. Why is it carrying a zero moment? The reason behind that is because in geometry, additional attributes, nonlinear hinges, it was by your own definition that you defined a certain limitation for R. And in MYZ, you can see that R is limited to this value, to almost 9.5 times your elastic R rotation, meaning that if you surpass this value, the hinge will no longer carry anything, which makes sense because in this case it would basically, like, I don't know, it would basically fail the connection, so it shouldn't carry any moment. So I don't know. This is a part of the definition. Now, you might be interested in seeing how this 10,000 force actually causes the partial or the full collapse of the structure. And this is really interesting, and this leads me to the second part of this video, which is going to be the pushover analysis. You see, the pushover analysis was created to push the structure up to a certain displacement and see where the structure might fail, to identify the weak points of the structure and make sure that there is no progressive collapse in the structure. Basically, that the collapse of that point should not put the entire structure in jeopardy. So to do that, and this is my second point of this video, you basically add a new model analysis because you want to unlock all kinds of dynamics, which is your basic unlocking thing. 10 modes, I don't know. I'm not really sure if this structure can withstand 10 modes. It's just 3 bars. Okay, I'll just leave it for 10 modes. I don't know. I think it will warn me because the structure is too simple to have 10 modes. I'm going to make me a pushover analysis, meaning I will gradually push the structure to a certain direction until it fails. Now I'm going to push me one of those nodes to the right. Now I'm going to choose this node, which is node number 2, and I'll push node number 2, I don't know, 200 millimeters to the right, just to like make the structure fail. So in the pushover analysis, I select node number 2. I want to push it in the UX positive, and I'm going to push it 200 millimeters. I'm not going to make any P delta stuff because I've explained that before. You can see the video which is linked above, but I want to not include geometric nonlinearity into account. Of course, you can do now a geometric / material nonlinearity, but this makes the entire thing a little bit too hard. I click on that now. I run the analysis, and let's take a look. Well, lo and behold, yes, the required modes 10 is too big. Only 8 modes can be found. I told you that the structure is too simple for too many modes to be included. You can see that the structure is struggling because you're dealing with material nonlinearity now. So, I mean, yeah, sometimes it struggles to deal with this. So, okay, let's take a look. Let's go to pushover and take a look on what is happening. The first thing is I want to go to pushover plus, which is the envelope, because I want to normalize stuff and I don't want it to like break my analysis. So just open the deflection shape. I cannot see that. I'm just quickly normalizing stuff because I want to see whatever is happening. So I go to pushover now, And now you will see how the structure gets pushed over by a certain deflection. So if you click on push over and go to the beginning, you can see that in the beginning there is no deformation at all. Okay, so a quick update. I think that my 200 millimeters actually broke the analysis. Now I changed my pushover analysis to a smaller value, to 50 millimeters, just to make sure that this doesn't break my analysis. Well, we learn from our mistakes, don't we? So if I click now on results, diagrams for members, and click on MY just to show you, and click on normalize, you can see that you have a certain moment diagram in the beginning. Because in the beginning, it's only a small push, the deflection is very small, so basically you don't see any problem. Of course, I need to quickly check out my deformation, scale that, and normalize the scale, and everything seems to be fine. So in the beginning there is no deformation. I'm just gonna double check the scale just to normalize here. So I go to pushover plus and normalize everything because I want to normalize to the maximum that I have. Going back to my pushover and discussing this, you can see in the beginning I have almost no deflection, which means I have no moment. When you increase this step by step, you can see that basically deflection starts building up, as you can see here, and the more deflection you have, the more moment you have, because I mean, when you increase the deflection, your moment increases, of course. So I just going forth and forth, we're going and increasing the deflection, and you can see that the deflection was not enough to cause any sort of plastic hinge. I was unable to see this, and this means that my pushover analysis was unable to actually push the structure enough for it to fail. So I have to modify my pushover analysis again because 50 millimeters was too small. So let's repeat that. Okay, so after some grueling amount of trials, far more than I want to admit, to be honest, I was able to find a good range for displacement 250 because I wanted to show you when a structure fails. Because in the other ones it was either too high, which means I wasn't able to see the structure failing, or it was too low, meaning that the structure didn't fail at all. Anyway, so I have my 250 now. After I run the analysis, let's take a look on the results. So if you click on this case component now, and you are on pushover, if you click on pushover case and click on case components, now you can see the displacement being applied. You can see that the node here at 2 gets pushed with each case. You can see that the pushing is happening step by step, and you can see that the displacement increases. And of course, on the last point, the displacement is around 250 millimeters around. Of course, it's more because failures happen in the structure, but that's besides the point. So let's take a look on what happens with the structure while we are increasing the pushing over of the structure from the right side. Now remember, I have defined two plastic hinges. I've defined a plastic hinge at 3 and a plastic hinge at 4. The reason why I defined the plastic hinge at those nodes is because I know that the moment diagram is maximum at those 2 points. And I know that the moment diagram is not maximum in the center, so that's why I ignored applying a hinge in the center, because there is no moment at the center for the current configuration. Of course, for structures, you should apply a hinge at the edges of the beam or any member and at the center of any member. Now, this is why I told you robot doesn't have a quick material nonlinear model, because this is only an approximation. Now, because we know for a fact that the maximum moments happens at those hinges, we are able to apply some internal hinges there. However, in real nonlinear models, the software itself should detect where the plasticization happens, and it should apply a hinge itself. And this is where robot has a small weak point. You see, robot, I mean, I don't know if it's a weak point or not, to be honest. I think it's a good thing. You see, robot relies on you, my dear user and viewer, to implement internal non-linear hinges in the positions where you think plasticization is going to happen. Now, this might be a weak point for robot as a software-wise, but truth to be said, in my humble opinion, I think this is a good thing because it makes you think exactly where you expect the structure to fail and apply plastic hinges to see which of those points actually fails first, and check if the structure is able still to hold itself, or it basically gets unstable and just falls down. So I just continue with this. And you can see that with each subsequent moment increases, you have two plastic hinges. You have 3 and 4, and you can see 4 has more moment. So I think 4 will fail first. You can actually see that suddenly moments in 4 don't grow. It actually somehow reaches stable position, and then I think it should snap depending on the definition of our plastic hinge. Let's take a look. Yeah, it snapped. You see, the hinge at 4 snapped, because in our definition for those nonlinear hinges, to show you very quickly, we actually, in the definition, you see that it snaps. You can see that after a certain position it snaps and then it goes to 0 again. So what I'm expecting is, I mean, this is beautiful. What I'm expecting is that, oh, look at this. You see it totally snapped to 0. This is exactly what I want to see. This is gold, to be honest. You can even see that this plasticized, it's not snapping yet, but it doesn't increase in moment. And you can see that it didn't snap. Now, of course, the question is, when did it plasticize and why? To answer that, let me show you. I'll just open the labels now, just to make sure, and to show you when it plasticized. So let's take a look. In the beginning, there was a linear growth. Increase was totally linear. You can see it's increasing by fives, 40, 45. You can, this is perfect. At 50, things changed. You see, before 50, it was increasing by fives. You can see that. You see 5, 30, 35, 40, 45, 50, but at 50 something snapped and it stopped increasing. It starts increasing by ones because, I mean, now why did the slope change? To remind you, the slope changed because this is what you have defined, or this is what we have defined in nonlinear hinges. And once again, to repeat, if you go here, click definition. Oh, sorry, I just think I messed up. You can see that here it was increasing a lot, and here it was increasing very gradual. So here it was increasing the fives, and here it's increasing the ones, basically. You can see that this is exactly what happens here. It's increasing by ones. And what happens, that ends up happening is, because it is unable to increase, other parts of the structure start to carry this load. You can see that in the beginning the increase was equal in all the structure with similar values, and when that snapped, those things started to skyrocket because this is unable to carry anything, so its other colleagues are going to jump in for it and start carrying, and you can see that those moments skyrocket. I mean, take a look. It was here increasing by eights. So I mean, look at this. This was like 56, I think. Yeah, 56, and then 62 or 64, and then 72. Yeah, it was increasing by eights, and this was increasing by fives. Now, when this reaches its plastic region right now, you can see that suddenly it skyrockets, because if you click now, this increases by 1 and this increases by 10 instead of 8. So suddenly, whatever this is unable to carry, this would carry for it. And you can see that things skyrocket from now. You can see now it increased 18 here, and this increased on 1. It was increasing by 8, but now it increased in 18, the left column, because the right column is unable to carry anything. And of course, this increases until suddenly the right column snaps and goes to 0. In that case, everything explodes, basically. Now, what do I get from this after I see this? I get from this that point number 4 is the first point to a snap, and I know that this is now the weak point of the structure. The failure will commence from here. And of course, you have to do a deeper analysis for the type of failure mode that you would have once point 4 snaps. Now, of course, the question once again was, what is so special about the 50 or 50 moment here? What's so special about this? Well, it turns out that this is the plastic moment of your section. Let me show you very quickly. You see, I did some calculations beforehand for the W10 by 12 cross-section. I took the IY, the elastic modulus, the F field, and C, and I tried to calculate from the section modulus and plastic modulus, and this is also found in this reference here, which is section app, etc. You can copy this if you want. This is the section definition and the section. Those are the section parameters of 10 by 12. I've taken those two things from that reference, and you can see that the plastic moment, which equals the plastic section modulus multiplied by the yield stress, is 51,300 Newton meter, which is almost 51. And you can see that at 50, before 51.3, everything is fine in this. Everything is working perfect. You can see it's a linear behavior. After 51.3, suddenly things snap, and there is no more linear increase here. Things go differently, and the increase changed. And of course, the other forces are getting loaded more. Of course, at the point when it snaps totally, it goes back to 0, which is amazing to see. Of course, you can animate this, which actually is, once again, really amazing. I personally love that. I mean, this is gold for me. So I just start that and just enjoy basking in the amazing feat that is Robot. I know this is a simple frame, and you might want to have a full structure with pushover and nonlinear nodes, but I needed to have a simple frame to just for you to grasp the implications of whatever pushover is with nonlinear hinges. I will have a different structure, a full structure, where I will show you how you can predict the uh, how can I say this? The collapse mechanism and the collapse chain of the structure, also predicting where you should basically make sure that you have sufficient strength, because at some points you will lose the stability of the structure, and this will cause failure. I can actually show it to you here. I mean, take a look. If I apply two hinges, I apply two hinges on those both supports. Now, if my intuition is correct, I think the structure will collapse. Let me just try run that. I think it should warn me that, not really sure, but I think this should warn me that the structure becomes unstable, right? Because if those two things yield, then there is nothing stopping rotation. I think so. I don't know. Let me just check. It's struggling in my point of view. It's struggling because I think it should be unstable. Oh, it did. It did work. I'm surprised. I wasn't expecting that. I was expecting it to give me an unstable structure. It is stable. How? Oh, wait. Yes, it's still stable. Yes, it's still stable because, okay, this makes sense now to me and shows to you the insights you gain from such things. I stand corrected. It's not unstable, and I'm not gonna video edit this. I want you to see this because I wanted to see my thinking process. Like, I'm surprised. I thought it should be unstable, but it isn't. It isn't unstable because once what happens here is not that the entire fixed support snaps. What happens is that the ability of the point to resist moments snaps, which means that suddenly your fixed support becomes a pin. And this is perfectly stable for a pin structure. And this is the reason why it didn't get uh, basically totally unstable. What happens if I increase? Now I really want to see something. Give me a second. I want to explore it. Of course, you might be interested in this, and you might not. It depends. Give me a second. I want to try something. So let me just add some hinges here. I want to see what happens if I uh, force all hinges to yield, which will make this a house of cards. Because if this yields and this yields and this yields and this yields, then all those hinges yield, which will create a house of cards effect, which will be unstable. So, and I will add me a ridiculously big displacement in the pushover just to like test the theory here. So 500, okay. I just want to see if it actually feels the instability or not. So I want to see. I'm really surprised if it does. Oh, look at that. Oh, wow, look at that. Robot actually sees that. Oh, now I'm happy now. Now I'm genuinely happy. Like me as a researcher, I'm now happy. And it tells you its instability RY, of course, because now you have plasticized everything. Wow, this is gold. It's different from what I do in ANSYS. ANSYS is basically or Abacus. Those are softwares used for research. The kind of stuff I do when I'm doing my research as a assistant professor. But for now, I'm just gonna say very confidently that I think Robot is very good in terms of nonlinear material characteristics, but it needs user input, and this is why I love it, because it's good for you to have user input. This is what I exactly want. I want engineers to feel their structures rather than just blindly obeying whatever the software says. So, okay, I think this is a good segue to my next example. Going on to the next thing I wanted to show you a very simple beam. Now, I know you might not like the fact that I'm using simple structures here, but the reason behind that is because I don't want to start with a full structure without having a simple structure first where you understand the principles of those hinges. Full structures will come in the future, believe me. I will be doing a water tower, for example, or whatever it is, and I want to see what will fail first and how. So this is something I am personally interested in seeing. With that being said, I'm just going to make me a simple beam like this. And this time I will make a beam that is connected to I don't know, a bar like this. This beam alone, if it's on a pin, well, this would be unstable, obviously. But if I have two pins now, this beam will be stable, meaning if you just run the analysis, you would have a carried simply supported beam, which makes sense. I'm not gonna release anything. My goal is not yet to release. I just want to see that it's stable. So I will make a pushover analysis on this one, pushing it down. But before I do that, I will add here an axial hinge here because I want to see if this thing yields, and I want to see what happens if it yields. Okay, so I'll just go to geometry, additional attributes, nonlinear hinges, and now I will click an axial hinge. I want it in this point. So now I have an axial hinge here, and now I'm gonna basically run me a pushover analysis. So I'll just go to model first of all to unlock the pushover analysis. I'm using 10 modes, but I don't think that simple beam will have 10 modes. So I'll just accept that. But of course, Robot will warn me that, hey, your beam doesn't have 10 modes. So what do you want me to do? Wait, I want pushover, but I forgot which one I want. So what's the node number? Okay, it's node number 2. All right, so let's go here. I want node number 2 to go in the Z down for, I don't know, 100 millimeters, just to try that in the beginning. So let's, I don't know, let's run the analysis. I'm expecting instability if it yields. Its required number of modes is too big. I know, yes, I accept that. Okay, it seems everything is fine. It's running. Of course, it takes time. Pushover analysis takes time. There's iteration stuff happening. So, I mean, while it's running, I want to tell you my goal. My goal is to see if this one will yield in axial force, and if it yields, then you suddenly have an unstable structure here. I forgot actually to check how the model for axial forces looks like, so while it's running, I want to see that very quickly. So there is the axial hinge. Let's check out the definition. Oh, it took really long. I'm surprised. So this is Fx. Yeah, it seems displacement versus force, linear until a certain thing, and then it goes to nonlinear. Yeah, and then it snaps. So there is snapping in this. You can see also that in compression it behaves differently. But okay, fine. Let's take a look. And let's see if it snaps or not. I'm not really sure. I have to check. So okay, let's just let's just see the pushover analysis very quickly. And how do I know if it snapped? I know if it snapped if I go to results, diagrams members, fx. This is how I know if this thing snapped, because now I have axial forces. So I basically go to parameters, differentiated, filled, and labels, just to see. And now I'm just going to see what happens at the end of my pushover analysis. Did it snap? Okay, let's see if it still goes on. So each step goes on by 1. It's increasing linearly. There is nothing. Okay, it didn't snap, it seems. So let's take a look back. It was increasing by 1. Yeah, I don't think it snapped. So my pushover was too low. So let's go painstakingly increase it to 250 just to just see what happens. So yes, whatever. Let's run it again. This is once again a trial error situation because I don't know exactly, and I didn't calculate. I should have pre-calculated what the possible breaking point or the possible deflection of this is by calculating PL over AE, but I didn't. So I'll just wing it and see whenever I can make it snap. So let's take a look. Did it snap? No, it didn't. Oh, it snapped. Wait, did it? It snapped? Okay. Why? Let's take a look. So let's go back. Yeah, I'm investigating as we say. So this is like, I don't know, let's click. Okay, I have 16, 50. Okay, it's increasing by 17s or 16s. So this is increasing by 17s. So the next point should be 48 or something. So let's see. Yeah, 38.9. Fine. So next one is 100, right? Yeah, 100. So it's increasing by 17s. It's increasing by 17s until a point. Let's take a look here. 335, 419. Let me see. It's still 17s. Okay. Okay. And it just suddenly snaps. I think that I'm not able to catch the actual point of snapping in this position. I'm not really sure about that. Is that true? Let me just check again. So let's click again on pushover analysis and go to 300 just to make sure if it actually snapped or not. So let's take a look. Calculations again. I'm surprised why it's not. I'm surprised why it didn't go to unstable structure. This is something that is annoying me slightly, but I don't know. Let's click. So it's increasing linearly as we are expecting, and suddenly it snaps, right? Yeah, it snapped here. It snapped at around 415 kilonewtons. Yeah, so I think it snapped, and this is perfect proof that it's not. Now, what still remains for me a mystery is why is this not stable? I think that you still see some sort of uh, how can I say this residual force here that robot couldn't shake, and that's the reason why this is still stable, because theoretically speaking you have a small force here, and this small force seems to keep it stable. I'm genuinely surprised about this, but remember, yeah, I mean the what are we even doing? The deflection is all over the place. I mean, take a look at the deflection here. It's it's 1 meter. Like no, this is 1 meter. This is beyond unstable. But of course, robot has limitations in that regard, so I'll just accept this as is. So yeah, that's everything what I wanted to talk about nonlinear behavior, nonlinear material behavior. I hope that you enjoyed the video and that I earned a subscription and a like and a comment of that for that. If you have enjoyed the video, of course, please like, share, comment, and subscribe, especially subscribe because it increases the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.